In this video, I will present the paper A New Look at Cell-Free Massive MIMO, Making it Practical with Dynamic Cooperation. And this is a presentation from PMRC 2019. And I'm Emil Björnsson, I'm from Linköping University, and this is a joint work with Luca Sanguinetti from the University of Pisa. So let's first talk about massive MIMO and cell-free massive MIMO. What is that? Well, let's talk about cellular networks where we apply massive MIMO. Then we have base stations with massive number of antennas, 100 or so. And then we divide the coverage area into many different cells, each one with the base station having a lot of antennas. In a network like that, you as a user will be in one of the cells and be served by that base station. That means that each base station is surrounded by users. In the cell-free case, we are instead taking the antennas and we spread them out over the coverage area. That means that each user at a particular location will be surrounded by antennas instead, and there is no cells in a network like this. So there is a massive number of distributed antennas. That's why we still call it massive. And the connection to massive MIMO is essentially that we have a large number of antennas, which is much larger than the number of users. And we can deploy this in a large or a small region. And you see all of these antennas are connected to a station that is controlling them so they can serve the users coherently in the uplink and downlink. And the connection to Cloud RAN is that is a way of implementing something like this, having a cloud computer somewhere that is taking care of the control of things. And then depending on how you implement things, you can distribute the processing over these so-called access points or APs, or put a large fraction of it on this cell edge cloud computer. And there's also many other names for this. So in the keynote at PMRC, Magnus Frodig from Ericsson was calling these things radio stripes, and they have a certain concept for that, where you're putting all the antennas within the cable. And there is other names such as distributed serial massive MIMO, for example. But let's stick to the name cell-free massive MIMO in this presentation. The name cell-free massive MIMO was coined in a paper called Cell-Free Massive MIMO versus Small Cells. And in that paper, they made a number of assumptions. They have access points or APs serving K users, that is all the users in the entire network. Then they must estimate the channels to all these K users. They must compute the beamformers, how you transmit in the downlink and how you receive things and rotate the signals in the right way in the uplink to make a coherent reception and transmission. And they must send all of the K users' data over frontal links from this central processing units to the antennas at the access points, and we need to do that for K different users. So the frontal capacity needs to be proportional to K. And in the same way in the uplink, when you have received something, you need to send it for all of the K users up to the central processing units that can finish the decoding of the signals. And the number of power control coefficients that you need to select is also proportional to K. You have K users in the uplink, and you have K users that you need to transmit to from every access point in the downlink. The problem with that is it's not scalable to build something like that. So we cannot let the number of users grow large, for example. Take it to infinity, then the complexity will become infinitely large, and the frontal requirements will also be infinitely large. So how can we solve something like this? Well, actually, we already have a solution. We need to go back to the network MIMO literature, which is almost 10 years old now. So I wrote a paper in 2011 where we were proposing something that we called dynamic cooperation clusters. And later I was describing it in more detail in my book from 2013, a book called Optimal Resource Allocation in Coordinated Multicell Systems. So we didn't talk about cell-free networks at the time, but the principles are the same. So in my book, I said that dynamic cooperation clusters is enabling unified analysis of anything from interference channels to ideal network MIMO systems. But in the original paper, we would like to have a scalable implementation of network MIMO, which was the name that was used for cell-free networks at the time. And this is a figure from the first paper where we're illustrating that we have a number of access points that are spread out We illustrated them at base station at that time, but it's the same principle. And around them, there is a certain area where they are serving the users, and there is an overlap between these different regions so that some users are served by multiple access points. And if you would make these circles very large, well then all of the users in the entire network will be served by all of the access points. But that is not the scalable approach. So that was why we started to draw it like this. And when it comes to dividing a network into clusters where users are served by some access point and not by others, there are two types of clustering that you can consider. There is the network-centric clustering, which was popular in 4G, but not very successful. So the idea there was that you are making clusters non-overlapping of access points that are neighboring to each other. So you say these three belong to the same cluster, these two to one cluster, these three to another cluster, and so on. And in that way, you're still dividing the network into bigger regions. So there are essentially cells with distributed antennas inside of them. And the good thing with that is that you only need to draw cables between these access points that are within one of the clusters. But the bad thing is that you're not really addressing the problem that there will be a lot of interference for users that are along the edges between the different clusters. The other approach is something that we call user-centric clustering. So here the idea is that every user will be served by all of the access points that can reach them with the signal power that is greater than the noise, so that we will serve it by everyone where it makes practical sense to serve them. And in that case, for every user there will be a region of access points that is serving them, and you see that they are partially overlapping. And that is what makes this a cell-free network, because we cannot just divide into cells by drawing lines between them. And this was something that we talked about in this paper from 2011, but it's also something that has been considered, for example, in the Artemis P-cell technology, if you read their description of what they implemented. So it is a known concept as well. And what we propose in this paper is to merge the cell-free massive MIMO concepts with these dynamic operation clusters. And in that way, we'll like to create a scalable cell-free massive MIMO system. So we would like to have a provable scalability. So in order to have that, we need to define what do we mean with a scalable network. So here's a definition. A cell-free network is scalable if the computational complexity and the frontal signaling of each access point remains finite as the number of users grow large. So how can we achieve something like that? Well, the starting point is how we are allocating the resources for pilots and data. So we consider a TDD system, or time division duplex, where we are sending signals in the uplink and the downlink within the same coherence bandwidth and coherence time. So the channels are fixed, and we can use the same channel in the uplink and downlink, which means that we can send pilots in the uplink. So the users are sending these pilots, and then every access point can measure the channels to any user from itself. So it already gets all of the channel state information that it needs to transmit to the users. And then it uses that for uplink and downlink data transmission. And if we say that there's tau c channel users within one coherence block like this, well then we assign tau p of them to pilots, and the rest tau c minus tau p for data, either in the uplink or the downlink. And our proposed solution is that each access point should serve at most tau p users. So one user per pilot sequence as most, which makes a lot of sense because you can't estimate the channels well to multiple users that send the same pilot because of what is called pilot contamination. So you only want to serve the one that reaches you with the strongest signal power on the pilots. Then you compute local channel estimates only for those tau p users. The complexity of that is proportional to tau p. And you compute tau p beamforming vectors based on those tau p estimates, also not proportional to the number of users in total, but only to those users that you're serving. And you select power control coefficients locally, and there's a number of ways to do that in literature, going all the way back to those original papers from 2011, for example. So as you can see here, all that we are needing to do is proportional to the number of pilots, but not to the number of users, which makes this a scalable approach. What we haven't solved so far is how we should decide which up to tau p users that every access point should serve. And that we have a mechanism for as well. So how do we select these so-called dynamic operation clusters? We call them dynamic because if the users are moving around, we can change which users that are being served by which access points. And we start when the user is accessing the network. So here's the user. It turns on, it sends a random access request to be served by the network. And it do it to the access point that they can reach with the strongest signal power. So it's sort of listening to reference signal that are sent in downlink and figure out which access point would I like to be my master AP. Then that access point is going to be responsible for serving the user. So we call it the master access point, and it picks a pilot that this user is going to be using. Which pilot? Well, it monitors all of the tau p pilots and look at which one of these ones can I currently hear with the least power, which means that there's the least amount of interference on this one. And I pick this pilot and assign it to the user. Then the access point is contacting all of the access points that are in the neighboring area, and it tells them, I will from now on serve this user with this pilot. Would you like to join me? And then all of the other access points can by themselves decide if they want to join or not. And we know that will be at least one access point serving every user. And what I'm illustrating here in step 3 is that the cluster is formed by saying, okay, it contacted these 5 access points, but it was only these 3 that responded and say, we would like to be part in serving this user. While the other ones were thinking that, no, the pilot power from this user won't be high enough so we can contribute in a good way. And if we have a mobility in the network, the user moves around, well then you can redo this type of mechanism from time to time. And for example, change the shape of the cluster or change which will access point that will be the master access point. In the paper, we are deriving new analytical results for example, the spectral efficiency that you can achieve in the downlink and the uplink. And I won't go into all the details in this presentation, just explain some of the basic things so you can understand the simulation that we've been running. So in the downlink, we have a spectral efficiency where L APs, that is the letter we're using, and each of them have N antennas. And the channel from all access points to user K is a vector then, HK, which will be L times N. So it's a long vector. But within it, we have one vector from access point 1 to the kth user, from access point 2 up to access point L. And we need to figure out which of these access points are serving the user. And we do that by having a diagonal matrix, dk, which is also Ln, and in this case times Ln, to make it diagonal. And then we put zeros and ones on them to decide on which users are being served by which access point. So for user K, you have ones on all the antennas on access points that are serving me. And then we derive a spectral efficiency expression. We have a pre-log factor, tau d, that is the number of channel uses per coherence block that are assigned to downlink data transmission. And we divide it by tau c to get the fraction of the coherence blocks assigned for downlink transmission of data. Then we have this 1 plus SINR expression. In the numerator, we have the channel from all of the access point, this D matrix that selects which of the access points that are actually transmitting to me, and then there is a collective precoding or beamforming vector from these access points. Here we have an interference term, and here we subtract what we have in the numerator, and here we have noise. And we see that the interference comes from transmission to all of the users, but then we subtract part of it from the user itself. The precoding vectors for every access point L that is serving user I. So for access point L, there is a set D that says these are the users I'm serving. And for these ones, we are selecting some kind of beamform vector. and could be selected anyway, but in order to control the power that we are assigning to the user, we are normalizing. We have an average power constraint, so we normalize the vector like this, and then we let rho IL here be the actual power that we're assigning. And how do we select the precoding vectors? Well, from this expression we can do it in any way we like, but we consider two different methods. One thing is maximum ratio. In that case, we just take the estimate that we are getting for the channel, H hat KL, and we put it in here. And then we consider something called SLNR, or signal to leakage and noise ratio precoding, which is some kind of regularized zero forcing method. And in that case, we take the same estimate, but then we rotate it using the inverse of a matrix. What does that matrix contain? Well, it is the interference matrix, or the covariance matrix of the received signal. So here we have a summation over all of the signals that we are transmitting to from access point L. Then we have the estimates, because we only know those ones. We are not involving all of the users here. Then we have the power that we're transmitting with, and then here we have the noise part. So these are the methods that we're considering, and in the uplink we have similar result, but I won't bore you with those ones in this presentation. Let's instead go to numerical result. What we are considering here is that we have an area of 2 kilometers times 2 kilometers. In this one we are putting at 400 access points uniformly at random, and also 100 users uniformly at random. And we use a typical microcell channel model because the intention is that the access point will be quite close to the users. And how do we create our cooperation clusters? Well, we create them in the way that we described, and we let the users access the network sequentially. So I'm assuming that there are 10 pilots. So the first 10 users that are accessing at random locations are getting 1 pilot each. And then I'm applying this principle, user after user, where they are getting the pilot that the closest access point thinks contains the least interference. And when it comes to downlink power allocation, what do? Well, we use a heuristic scheme that have been shown to perform rather well in a paper from ICC 2019, Scalability Aspects of Self-Remassive MIMO. So let's first consider the case where we have 4 antennas per access point. And I'm showing here the CDF, so that's the cumulative distribution function. So it shows how do the performance vary between the users when we put them out at random locations. The red curve here is when we use maximum ratio transmission, and the SLNR precoder, we have it over here. And what we see here is that the SLNR that is cancelling some interference is doing much better. So if we look at the median here, we have slightly below 2 with maximum ratio, and we are going up to around the double 4 with SLNR precoding. And when I looked at this, I thought, okay, we have 4 antennas, so yeah, of course we will get better performance when we can cancel some interference. But isn't this gap a bit too large? Is it something to do with what kind of channel set information we have? Because we actually are not sending any pilots in the downlink, so maybe the users don't have good enough information to decode the signals. So we were computing upper bounds by assuming that the users have perfect channel set information, and we see that the difference is still remaining. So it's very important to use something else than maximum ratio when you have multiple antennas. But what if you have only 1 antenna per access point? In this case, we have 1 antenna per access point, and maximum ratio is here, SLNR is here. The gap remains. And even if we add perfect CSI curves here, we see that we still have a large difference. So actually the SLNR precoder here works better even with 1 antenna. We can't cancel an interference, right? So what is going on here? Well, the tricky thing is that we have power constraints that are average. So when we have a good channel, we can either use more or less power, and when we have a bad channel, we can either use more or less power. And maximum ratio and SLNR precoder are doing this in different ways. Maximum ratio precoding is spending more power when we have a good channel and less power when we have a bad channel. And if we then just consider this in the product between the precoder and the channel, when we have one antenna, one access point, then for the user, we get an exponential distribution with a very long tail. So it could be very large, but it can also, with high probability, be very small. If we do the same thing with SLNR, it actually cuts down on the power when you have a good channel and spend more power when you have a bad one. And that way you get a distribution here of the channel gain that you're having, that is having a support that is limited. So it's all concentrated down here. And actually the average value is slightly smaller, but this is very positive as soon as you put more than one user into the network, because then the interference won't vary as much, and that is something that you benefit a lot from. Let's go to the uplink. And in that case, we are considering regularized zero forcing, or RZF, which is the counterpart of signal to leakage and noise ratio precoding in the uplink. And what I'm showing here are three curves. I have only one antenna per access point. And here is maximum ratio precoding. All the access point is serving all of the users. And this is what was considered in the first papers on self-free massive MIMO. Then we go to the blue curve here, which is regularized zero forcing with only one antenna. And now it's scalable because we are only being served by some of the access points, the ones that went through our way of forming dynamic operation clusters. And then the last curve is when we use also regularized zero forcing, but we are using all of the access points to serve all of the users, which is not scalable. What we observe here is that the price for scalability is very, very small. It's only a few percent that we are losing. However, the gain over maximum ratio, which in this case is not scalable, is huge. So what we managed to do in this paper is to both create something that is provably scalable and can outperform the original unscalable form of self-free massive MIMO with a huge margin. We are almost doubling the performance here of the users. So let's sum up this presentation. It's called A New Look at Self-free massive MIMO, and that was what we did by combining self-free massive MIMO in the original form with dynamic operation clusters, because the original form was not scalable. And the new contribution is that we are of course putting these things together, but also we are creating an access protocol to form the clusters in a way that performs very well. We derive general spectral efficiency expressions that you can find in the paper and that can be applied together with any corporation clusters. And we discovered in particular that signal to leakage and noise ratio precoding and regularized zero forcing outperforms maximum ratio a lot, even if you only have one antenna per access point. And there is a journal version online called Scalable Self-free massive MIMO Systems, where we go into all these things in further detail. And there is of course open problems related to this type of things, because it's not so hard to create a self-free massive MIMO system that is provably scalable. That was what we did today. But to do it and at the same time get a good performance, that is a challenge. So getting smart distributed power control systems, in particular in the downlink, that is something that is challenging. And also to utilize the structure of the front haul to build an efficient network. That is something that we would like to do as well, to look into how the capacity of the front haul can be best utilized. So this is the paper, A New Look at Self-free massive MIMO.